Okay, so thank you very much, and thank you for the open-mindedness of the organizers to let me speak about this topic. And it's meant as an introduction, so it's rather pedagogical. And the goal is to prove a classical theorem, but with various improvements possible. That is, I probably won't do it, namely prove Holmgren's theorem in a sort of general version. And what it says is this, that we have a differential operator dx alpha. So here I use the multi-index notation, and also I write capital D for 1 over I, the partial derivative, so that on the Fourier transform side, capital D corresponds to multiplication by xi. And Holmgren's theorem applies to operators with analytic coefficients. So in some set U, and U is inside of Rn, omega here stands for real analytic. And the statement is that, say, in the simplest setting would be if Q is equal to 0 in omega and U is a distribution and the support of U as a distribution is contained in a set where, say, f of x is greater or equal to 0 and f is a C2 function in U, then this implies that the boundary is characteristic with respect to f. So this implies that P of x differential of fx is equal to 0, and for x where f of x, sorry. If I have a, so I need to be a little careful, f is Z2, so if x naught is such that f of x naught is equal to 0, x naught is in the support of U, then, so maybe I should say if this is true, then this implies that P of x df of x is equal to 0, where P is the polynomial obtained by taking the highest derivatives and replacing them by xi. So this, the standard theorem of Holmgren, I think, applied to the wave equation. And what it said was that if a solution vanishes in some set, the boundary, if there are points in the support of the solution on the boundary has to be characteristic. So for instance, the solution has to be supported in the cone. It cannot be supported in a cylinder. That's what it means. And there are various generalizations that I may or may not discuss. But I would like to prove it. And the plan of action is the following. Plan of action is to consider solutions which are in the tempered distribution. So just to remind you, the Schwartz class is the set of all functions which decay faster than any polynomial. In all the derivatives decay faster than any polynomials. S prime is the dual space to that, so here you can take derivatives. If I have US, I will now define it. It's nothing really difficult. The singular support, the analytic singular support of U is the set of all points. Now in Rn, it's a global situation such that there exists, it's a complement of the set of points such that there exists a neighborhood U, a neighborhood of X, so that U is in fact analytic in that neighborhood, real analytic in that neighborhood. And being real analytic in this neighborhood means that every point there has a complex neighborhood to which this function can be extended as a holomorphic function of n variables. So this, there's nothing more than one can say. This is the singular support. It's a closed set because this condition is clearly open. And that what we'll introduce afterwards is another object.
Maciej?
Yes, please.
Sorry, because so you could think about the singular support replacing C of X
That's right. So then it's a singular support without an A. Yes. But I am working in the analytic category here. So we will now introduce, so this is the object which has a long tradition, but I will call it the analytic wavefront set. But since I will only talk about analytic wavefront sets, I will skip A. I will look at the set, which is a wavefront set of U. That is a subset of Rn cross Rn minus 0. And I will define today the main thing about this set is that if I look at the projection of x and psi, x being in Rn, psi being in Rn minus 0, that goes x, then pi of this analytic wavefront set of U, well, I'll put A here, is the analytic singular support of U. Sorry? Yes, this is a complement. It's for complement. It's a C like that. It's like from old style books. Yes. No. Yes, it's a complement. Yes. Huh? No. Okay, that's a complement. Huh? And you know what we are going to prove then is, but using methods which are, all of these are more complicated methods than needed to prove this theorem, but the whole point is to introduce the sort of a general picture. What we will now prove is the analytic wavefront set of U. If I have an operator like that, an operator with coefficients that are analytic, the analytic wavefront set of U is contained in the characteristic set of P union, excuse me, with the analytic wavefront set of PU. And characteristic set of P is just a set of x psi different from 0, such that A alpha x psi alpha is equal to 0, alpha is equal to m. So what this means is, for instance, if I have an equation PU is equal to 0, this means that this analytic wavefront set is contained in a set of zeros of this function. So, yes?
Is this identical to the unique continuation, or is this almost the same?
It's a unique continuation theorem. It's probably the first one. Well, not the first one, but for operators of higher order, let's just say. Yes, so I don't, to be honest, know the history too well. I believe Holmgren proved it maybe for the wave equation. The general version was proved by Fritz John in the 50s. There are many improvements that I maybe will get to, but I want to just state this simplest thing. You could indeed, because what it says is that, you know, if you have a surface which is non-characteristic, you can continue the equation across, the solution across that surface. That is correct, yes. So, and you see, and the next thing we'll prove, which is, you know, my favorite theorem in microlocal analysis, namely the Kashiwara's watermelon theorem. Watermelon theorem. And Alex promised me a prop for that. And what does it say? Well, I'll state one version just to support of U. If support of U is contained inside of x1 greater than 0, say, and there exists some psi, always this is different from 0, such that x psi, so let's say 0 psi. So here is my support, and here is the point 0, but could be any point on this line, is in the wavefront set of U. Then this implies that x psi plus t e1 being the first basic vector, you know, 1, 0, 0, 0, is in the wavefront set of U for all t. Of course, if it happened that xi aligns with E1, then we have to exclude 0. But it's just the invariance of that. So now let me just show quickly how does this watermelon theorem imply Holmgren. Well, suppose we are in this situation here, and let me, f here can be replaced by an analytic function because all that matters for this condition is just the second Taylor coefficients, and I can always add a quadratic term to replace f by an analytic function. When I replace it by an analytic function, I can make it, if the derivative is not 0. If the derivative is 0, then there's nothing to prove. Sorry, there's x not here. There's nothing to prove. If the derivative is non-zero, I can replace it by x1. So I am in this situation here then, that support pu is equal to 0, support of u is inside of x1 non-negative, and let's say 0 is in the support of u. But then, of course, u cannot be real analytic at 0 because the support is on one side of this hyperplane. So clearly, unique continuation for analytic functions would be violated. So what we know is that this implies that 0 is also in the analytic singular support of u. But this, of course, implies, because this mysterious set, maybe not mysterious to anybody, but not defined yet in these lectures, the wavefront set, since it projects to the singular support, this means that there has to be xi, which is in it, xi. So this implies that xi, there exists xi in Rn minus 0, such that this is in the wavefront set of u. But now I should say that this set here has properties which I did not mention. This wavefront set is a closed set, and it has the property that it's homogeneous in xi. So I know now that any point like this is inside of the wavefront set. But then I can take t to plus and minus infinity, and this means that this direction is in the wavefront set. This is an elementary thing, but you see, this set is homogeneous, so I can write this as t psi over t plus E1, yes? And I can take t very large, it's a closed set, so this means that the E1 direction and minus E1 direction have to be in the wavefront set. But then we use this. Pu is equal to 0, so there's no wavefront set here. So this means that what's in the wavefront set of u has to be in the characteristic set. But this means that this implies that Px plus minus, though it doesn't matter, E1 is equal to 0. But E1, of course, is dx1, which is the defining function. So this is why this is kind of a very conceptual way of seeing this theorem. So our first task then is to, since we already defined the singular support, analytic singular support, there's really nothing to it, we have to define the wavefront set. And there are many ways to do this, but I will follow a definition which was first introduced by quantum field theorist Bross and Jagolnica in the 70s. It was first defined for hyperfunctions by Sato, Bross Jagolnica, a definition of the wavefront set. So for that, we have to introduce a certain something called the FBI transform. So FDI, even though this transform occurs in many places under different names, but in this context, because of Brozia-Golnic and Fourier, it's called the FBI transform, as I said. So this is for Fourier. Well, I'm not going to write it, but it's also called Bargmann transform. It's called Gabor transform. It's called Siegel-Bargmann transform. But it's a matter of context. And here it will be a transform which depends on a small parameter, which takes tempered distributions to functions e to the minus 1/2 over h, z minus x squared, u of x dx. And there's, for reasons that there's some constant which I will not specify, and we put, for this discussion, it's actually not important, but it will become important later to have this prefactor. So this is a transform. Now let's look at this phase, z minus x squared. What is the minus 1/2? What is that? Well, it's minus 1/2, real part of z minus x squared, plus real part of z minus x times imaginary part of z, plus 1/2 imaginary part of z squared. So this factor, this is just sort of something you could take out, because that's just depends on z. So the interesting part in integration is this. And what happens here is here we have a Gaussian. So this function, if I look at the real part of it, what it looks like here is x, here is real part of z rather, this will be the x-axis, and this function concentrates on a Gaussian, yes? And as h gets smaller, this Gaussian gets tighter and tighter. And this term now, and except that I forgot something important, I forgot an I, thank you, otherwise, yes, thank you, I forgot an I. So if I would look at the real part, this oscillates, So it's sort of, we have an envelope like that, and then we have oscillations which become more and more rapid as h gets small. So what this means is that this transform first localizes you to a neighborhood of real part of z, and then we take the Fourier transform of it, and we look at it at frequencies 1 over h. So h is the wavelength, if you like. If h gets smaller, I don't really want to use colored chalk because then I'll not be able to erase it, but this gets tighter, the oscillations get more rapid. So this is why this sort of measures your function both in position and in phase space, because it tells you, it sort of localizes you and then takes the Fourier transform. Of course, the uncertainty principle tells you we can't really understand a function pointwise in position and momentum or frequency, but this is one way where we can get it pretty closely. And then maybe I should say a few things, just basic things. So one thing, using this Fourier transform and the Gaussian, I leave it as an exercise. Plancherel's theorem. Plancherel implies that THU on L2 phi, which I will define, is equal to, and this was why the constant can be chosen so that this is so, L2 of Rn, where L2 phi is the weighted space Cn with respect to, we have to take out this guy so that we eliminate this growth. If minus 2 phi over h Lebesgue measure on Cn. Sorry, this is the L2 with respect to that. And what happens is that one checks this using Plancherel that this is true. And that also shows that TH star, TH is the identity U on L2 of Rn. I should say that, you know, this is applied to U in tempered distributions. So of course, when I mean it as a tempered distribution, what I mean it then as that this is a distributional pairing. But of course, this function as a function of x is in Schwartz class with, you know, bells on, as they say, not in this country, but somewhere. So this is the FBI transfer. Yes, please.
I thought that U was defined on R.
Rn, yes.
Oh, okay.
So I'm integrating over Rn here, huh? And I'm taking it, yes, sorry. And I'm taking Z in C, huh? N, Cn. That's why real part of Z, imaginary part of Z. This is in Cn now, huh? So please, you know, interrupt me. I'm sorry if I... Yes, please?
Phi is the last thing.
Phi, where is phi? Oh, phi, yes, I'm sorry, yes. Phi, because you know, phi of Z is this. This is phi of Z. Is the weight. So this is a space of holomorphic functions, L2 functions, with respect to this measure.
And TH star is defined.
Very good, that's right. So TH star, of course, is defined using this thing, so absolutely. So by the way, I forgot to say an important thing. I did not type notes for this thing, but I have a sort of a edu. I wrote references for each step, precise references to specific sections and results in various sources for different things that I will be presenting. And also I did type up a proof of, which is basically Shestrand's proof of Kashiwara's watermelon theorem, but because it's for one thing, it's only in French, but yes. So now using this, we define the wavefront set, and we define it again using the complement. But to make things more straightforward, I write like this: x psi is not 0, is not in the analytic wavefront set of U, if and only if I put Z to be x minus I. Let's put x naught, xi naught. Z naught is x naught minus xi naught. So this is just a definition. There exists a neighborhood inside of Cn of Z naught and delta greater than 0, such that THU of Z has some decay properties. So when I do this, let me just make a comment here. If U is in Schwartz, then just looking at the semi-norms on this Schwartz function against which we are integrating shows that THU of Z is pointwise smaller than some negative power of n, some positive power. So this notation here means 1 plus Z square root, some positive power of Z, and then the factor coming from my weight, this leftover stuff that, you know, it would just come out. You don't integrate, you integrate in X. So this last piece just goes outside, and I call it phi of Z divided by H. If U is a Schwartz function, then this implies that this is less than or equal to, for every n, Cn, so these are exercises, e to the phi of z over h. The statement here is that x naught, psi naught, is not in the wavefront set if this point z naught has a neighborhood inside of Cn such that this decays exponentially a little better than this weight. And this is this little better. Here? No, I think for Schwartz functions, because of maybe my normalization, I don't need it. I could, but no. There's no decay in H. There's no decay in H. No, certainly not. Or certainly not, because look, it's after all unitary on L2. So, you know, it can't be, but it will be, we'll show that it's unitary. So this is the definition. Now, this definition was very attractive, but there's one thing that's already a little bit non-trivial, which is this, that it is not at all clear, at least not to me, just like that, that this wavefront set is radial, namely that you can multiply. My function u does not depend on h. H is just a parameter that we introduced. It's not obvious that this is radial. Yes, please.
Question. I mean, if you take this neighborhood to be
the neighborhood is tiny, and it's a tiny neighborhood.
So can you not always find a function?
Certainly not. Even no.
You're integrating over the.
Yes, but minus delta over h. I'm gaining something exponentially small. We'll see in a moment that.
I mean, this kind of estimate, naively, I would think it's for Z large or something like that.
No, Z is not large.
Right, so
Z is not large. It's just in a neighborhood of a fixed point, and this point corresponds to the point in phase space, which is x naught, psi naught.
the point is that C does not depend upon H.
Yes, of course. So whenever no constants depend on H unless specifically stated, all of this. So H here is a parameter built into the FBI transform.
So it's not H is allowed to go to 0.
That's right. So H, yes, you see, I'm so used to H being small that I didn't say. H is small. Sorry, thank you. I appreciate this. So please stop me anytime because, you know.
I mean, if H was fixed, this would be always true. You're allowing H to vary.
Oh, no, yes, of course, such that, yes, thank you. For all H, small. Smaller than summation. Yeah, thank you so much. I really appreciate it. Please don't hesitate to ask questions because I've been swimming in these waters for too long, and consequently, I will drown eventually. But so now, actually, you know what? I also forgot. I have it because it was small. That I wanted to. Maybe I'll say it now. You know why general relativity? Okay, because this I forgot to say. So in fact, the first, I started in this business because of a question motivated by general relativity. And the question was the following, maybe it doesn't ring any bells, but the question was, we study sometimes, you know, the quasi-normal modes for, say, black holes. And quasi-normal modes, in fact, that's sort of one characterization. They are solutions of the stationary wave equation with some, of course, appropriate variables and so on, which is smooth across the event horizon as you go into the black hole. And both for conceptual, but also practical issues of say, unique continuation and so on, it is then a natural question that in black holes, which have analytic metrics and so on, is that quasi-normal mode also analytic across the event horizon? And it boils down to a question which actually is extremely simple to state. At least, you know, the simplest model is the model like this. Lambda, for reasons, this would be the spectral parameter plus, say, dx2 squared. Event horizon corresponds here to x1 equals to 0. And question, suppose I have a smooth solution p equals to 0. Is it analytic across x1 equals to 0? So actually, I did not know how to do this. And so I gave a prize for the solution, a dinner in a 2-star restaurant. And it was actually the first prize ever that anybody actually clocked. And that was Claude Zully, who pointed out to me, as he said, I'm old enough to remember some stuff from the 70s and so on. And he managed to adapt some work, actually pre-microlocal analysis of Bolet and Camus, and showed that in some class of operators that, for instance, included some simple black holes, that my statement was true, namely, if this is equal to 0 and U is smooth, then U is analytic. But there was one funny thing about his proof was that it only worked when lambda is not an integer, which seemed completely ridiculous to me. And then actually, that was partly why I got interested in this business. And with Jeff Galkowski, we proved a general statement, which I will not produce here, using methods which are similar to what I'm going to talk about, but sort of, you know, and in particular for integers and so on. And then Peterson and Vashi showed how to use this microlocal result to show the analyticity of quasi-normal modes across event horizons for general black holes. I don't remember what class, you know, but some kind of black holes without any symmetries, but with analytic coefficients. What's Google Maps 2 stars? In any case, so unfortunately, I had 2 problems in general relativity on my list of problems that had awards. And the second problem was also solved by Peter Hinz. And also he collected the prize. So all the other problems are not in general relativity, I'm afraid. But this is an example, and why these methods are, to me at least, interesting. But let's go back to the FBI transform.
Can I just ask?
Absolutely, absolutely.
I'm still obsessed with this power.
Yes.
Because, I mean, usually smoothness should translate into polynomial.
No, okay. No, okay. So since you ask, I'll tell you. So this is a global estimate.
Yeah. So
this is a global estimate. If you want a local estimate, x naught psi naught, so this is an aside, is not in the usual wavefront set, if and only if the same thing is true, but you replace this by O of h infinite. That's what you are thinking about. But I don't want, you know, the best thing would be if you've never seen the wavefront set, and this will be the first one you ever see, which actually it is the first one that the world ever saw, because Sato defined it in the analytic category, not in the smooth category, but defined it in a much more complicated way. And, you know, speaking of applications, just if you survive to the bitter end, I will give a talk about applications to a problem in condensed matter physics. So now the first question is, why is this set? So first proposition, I will not, I think I gave a reference in my notes. The first proposition is, if x naught psi naught is or isn't in the wavefront set, this is equivalent to f naught, t naught psi naught being in the analytic wavefront set U for all t greater than 0. So in other words, this set is conic. This set is conic. And, you know, the proof is based on something we learn in high school, namely completion of squares, okay? And it goes, I will just tell you, it is convenient for this proof to remove, rather than think of z, think of x and xi, think of z being x minus I xi, and remove this horrible factor, but you lose something. I should also say one more thing. Well, let me just finish here. So remove this factor, and then this is just t h u of x minus I xi. And then you see, we can see what is the FBI transform of u x t xi. Well, that is, you write it, and you see that this is the same as me to the 1 minus 2h x minus y squared minus plus I over h t xi x minus y dy. And that I would call th u of x xi. So as you see that these two guys change via scaling in t. And actually it's convenient to write it yet another way, namely divide h by t, and here also by t. So this, if you like, would be, I change the Planck constant, but I multiply my Gaussian by some other factor. And now, you know, because I know, and I wrote it, but I won't say much about this, we have that formula that t star th, u is equal to u. So that means that t, and it works for this tilde thing as well. So there's some prefactors that I forgot here, you know, but I can write it as t star h th. That is equal to u is equal to t tilde u. So what you do now, you look at the composition of these two operators. Sorry? T tilde, yes, thank you so much, T tilde. You look at the composition of this operator. So I wrote it out, but you know, this is an elementary calculation based on completion of squares and doing Gaussian integrals, okay? And when you do this, you obtain the kernel, integration kernel of this operator. And what you see is that, so I wrote it, but I don't want if you really, but I will just write it, that the integration, this is given by integration against some kernel. So this now takes functions of x and xi to functions of x and xi. So this is some kernel x xi y eta v of y eta dy d eta. And then we can evaluate this simply by integration. And this kernel roughly has terms which are xi minus eta square over h minus x minus y square over h, with some decorations depending on t. But this means that it localizes you in this square way. And if you just manipulate it, it's believable. This Gaussian localization, both in x and xi, will show that if this thing has this extra gain of delta, so will this guy as well. So it's a straightforward thing, but it depends on sort of properties of Gaussians. How much time do I have? Sorry? 20 minutes, perfect, okay. So any questions about this? I can write down the formulae, but I think it's not so illuminating because, you know, it's completion of squares and observation that if you have a kernel, which is like a Gaussian, it's almost like resolution of identity. And once it's like a resolution of identity, your delta will stay there. If you have it for this guy, this is close to identity in some sense. It will still have this extra decay. Yes.
So the star there is with respect to.
It's a star, except yes, it's respect to now L2. That's right. This star, since I removed this phi, so it's now with respect to just integration with respect to Lebesgue measure on Cn.
You have to make the open neighborhood a little bit smaller.
A little bit smaller, but hey, who cares? I mean, it is a small neighborhood. Huh? That's correct. I need to make it a little smaller to take care of the sort of Gaussian things. Mm-hmm. But, you know, I want to say, because, you know, at first this definition, it's not obvious that, you know, it has this scaling property. But completion of squares and first year calculus, namely evaluation of Gaussian integrals, solve this problem. So now we have the first theorem, which is that the projection of the analytic wavefront set of U is equal to the singular support, analytic singular support, AU. So proof, so there are two directions, yes? So first I want to show that, say, if X naught is not in the singular support of U, then for every xi different from 0, X naught minus I xi, or let's put xi naught, then Z naught equals to X naught minus I xi naught, has a neighborhood such that THU Z is less than or equal to E to the phi of ZH minus delta over H. Namely, if I know that I have a function which is analytic in a neighborhood, then for all possible xi's here, I will have this property. Now, you may have asked yourself and answered also the question, why am I keeping this phi? After all, life was a little bit easier without a phi here. So why are we keeping the phi? We're keeping the phi because with the phi, namely with this phase function, the nice thing is that if I take U, which is a Schwartz function, this is a holomorphic function of Z. And we will get some mileage out of it. That's why I'm keeping this phi. So this implication is the easy one. Namely, if X naught is not in the singular support, so this means, what this means, which inclusion is it now? If X naught is, so this means that if X naught, if this is true for everything, so this means that a pi of the wavefront set includes the singular support, yes. But that's just, yeah. So how do we do this? What you do is, you know, that now U, let U be a neighborhood, a complex neighborhood, C of X naught. So X naught is real, but it has a complex neighborhood such that U is holomorphic in this complex neighborhood U. Okay? So then what we do, we simply deform the contour near this X naught, and take advantage of the Gaussian decay away. I'm not sure even if I wrote it, because no, because I only wrote the difficult part. So So maybe I did write something. No, because it's so easy. So, so how do we do this? Well, I'm going to write my THU of Z, and that's a modulo of these prefactors, which of course for this don't matter because we will be getting exponential decay. It's U of X, e to the minus 1/2, Z minus X square dx, and the over H. And the idea now is to do two things. First, deform the contour near x naught, so that you will gain an extra decay in here. Because if I'm going to, and then away from that point, I will have my Gaussian, which will give me my delta. So I now work Z is near x naught minus I xi naught. Xi naught is arbitrary, and I just need to change my x, move it in the complex. So I need to write, let's just write, if z minus x square, if x now is complex, this is equal to 1/2 minus, this is equal to minus 1/2 real part of z minus real part of x squared plus 1/2 imaginary part of z minus imaginary part of x squared. And then I have to get the imaginary part. Imaginary part, well, you know, it's the usual thing. It's just real part of z minus real part of x times the other thing, imaginary part of z, imaginary part of x. And the point is that I'm not going to do this, but I leave it to you as an exercise, that you can choose this imaginary part of z here and deform it into the complex, and you will see that you can gain exponential decay from that. So it's just a way of choosing the contour. So choose the contour. And otherwise, if we are away from z naught, real part from x naught, then we are away from real part of z naught, and then the Gaussian gives us this extra delta. So is this convincing? I mean, I can do the contour thing, but it's just, you know, there's no difference here between several complex variables in one complex variable. So I want to do the more interesting part. Yes, please. The draw. Okay, so the picture is like that. So this is C, this is the x-plane. I have here the real part, so real part of z naught, which is x naught, Yes? And then depending on the sign of xi naught, I do some deformation like this or to the bottom so that the sign is right to compensate for this, Something like that, yes. Of course, this is in all dimensions, but there is no difference. The interesting part is the proof of the converse, namely to, yes, please.
When you're doing this deformation, you're gaining something in your x naught.
I'm gaining.
It's not going away.
Yes, so all I need to do, I only care about the real part of this. So I look at the real part of this. And what I need to make sure when I expand it is that depending on, you see, imaginary part of z is close to xi naught. So I just need to make sure that I have a favorable sign of imaginary part of x. I mean, I can write it out, but it's you know. So I would like to finish by doing the opposite implication. And it's based on a cool formula, which I hope you will enjoy. So now I want to show that the opposite implication. So suppose that T, H, U, Z is less than or equal to E phi of Z over H minus delta of H for all Z near X naught minus, and here you see I can put omega any point on the sphere because we proved that the set is radial, huh? So this means that I only need to, this is, I have those, this is X naught. Well, I can't draw it. This would be now an imaginary sphere. And this imaginary sphere, any point on the sphere, I should have this. Of course, this delta is not uniform as I would go, as I would scale it, but I don't need to worry about that. I only need to assume it on the sphere. And what we want to show is that this implies that U is, and let's just call it holomorphic, near X naught. X naught is real, but I now think about it as a point in Cn. And that proves it's real analytic, which of course means then that X naught is not in the singular support, analytic singular support view. So this is the less straightforward part of the implication. And it's based on something which we call the Lebesgue inversion formula. And at this stage, against my usual preference, I have to switch to lambda equals to 1 over h. Reason being that I just cannot integrate in h. Well, I can integrate in lambda. So what is Lebesgue's formula? If I can find it. 1.6, 1.4, 1.5. Yes. So Lebesgue's formula. Well, actually, sorry. Before Lebesgue's formula, I'll show the following formula. If U is a compactly supported distribution, it doesn't really matter because all is local, and R is in 0, 1. And then we have the following actually inversion formula. Well, not inversion. We have the following formula: 2 pi minus f 0 infinity e to the minus lambda over 2 lambda to the n minus 1. That's why with h it would be much worse, right? Omega equals to 1 minus omega dz over lambda applied to t of 1 over lambda. So h is 1 over lambda. U x plus I r omega d omega. Oof. This is, well, so far it's nothing. I just wrote something. I defined UR. Okay? I defined UR. The fact is that, so proposition UR is analytic in Rn. So this is for R is between 0 and 1. You see, the reason is that we have decay. The factor here is minus lambda over 2. Here on the unit sphere, we know from those things that are written over there that this will decay like e to the minus r lambda over 2. and r is less than 1. So this integral converges absolutely. You get an analytic function. However, this family of analytic functions converges in the sense of distribution as r goes to 1 minus to u, my compactly supported distribution. Sorry? No, this T has this is the holomorphic one. This is, no tittle on this one. This is this one. So you see, this one has this growth. You see, but we are on the unit sphere. Imaginary part is 1. And modulus phi, remember, phi is imaginary part of z square over 2. Here the imaginary part of z is r times omega. So if I square it, I get r squared maybe, okay, r squared. So this formula, so let me first prove to you the theorem assuming the formula. It's very easy because you see, suppose I have this extra delta. If I have this extra delta, then if I have this implies that T1 over lambda u x plus I r omega is less than or equal to E r lambda r squared lambda over 2 minus delta times lambda. Lambda, mind you, is 1 over h. But this means that I have extra decay here in lambda, so I can actually go past r equals to 1. And once I can go r past equal to 1, this means that my limit now is also an analytic function. Or even more explicitly, simply this converges where you would complexify this x, because if you complexify it, you will get a little bit of extra growth here, but again, it's killed by this delta. So the key is to prove this inversion formula. And of course, any formula for distributions corresponds on the dual side by a formula for functions, smooth functions. So that is Lebow's inversion formula, which I found and then I lost again. 1.5, 1.6, yes. Suppose phi is a compactly supported function in Rn. And here is a formula. Phi of x is equal to 1/2 2 pi minus n, an integral from 0 to infinity, lambda n minus 1, e to the minus lambda over 2, d lambda, an integral on the unit circle of 1 plus omega d over lambda t phi x minus I omega lambda d omega. So this is a formula. You see, if you would pair it with distributions, make changes of variables, you would get this formula here. Huh? I mean, take some writing. So I gave a reference in on this little thing to. It's very clearly done in Hermanda's book, without need to study anything. So I have I have 5 minutes. Just let me tell you, I'm not going to prove it then. I was planning to prove it just because it's so much fun. I'll just tell you how the proof goes. The proof starts, like much in our business, with a Fourier inversion formula. Let me get the Fourier inversion formula right. X phi, sorry. I could not get my Fourier inversion formula right here. Psi, now I have to really see. So let's just put, for simplicity, let's put 0 here so that I can really get it right. Y psi minus epsilon y u of y d psi dy. And actually not y, but psi. And not y, but not for u, but phi. Okay. It's written here, but so you have this, huh? That's a formula, which makes perfect sense, no? And what you do, guess, you deform the contour in this formula. And there is some, you know, as I said, since I'm over time, I don't want to do it, even though it's kind of a fun calculation. But you deform the contour, so you write zeta equals to xi squared plus I, xi eta. And the main point is that this absolute value of xi, so absolute value of zeta, you want to define it as a square root of zeta squared. So you just have to make sure that you first deform the contour so that the real part of this stays positive, so that when you square it, so that you can take the square root. But once you do it and apply a certain amount of old-fashioned cleverness, you get Lebau's formula. Roughly speaking, xi becomes d lambda d omega, and this will become dy, will be the one which will give you the FBI transform, after some manipulations. You have this formula, you then dualize it, you get this formula for your distribution, and as I said, once you have this extra decay for all omegas, you can go past r equals to 1, and hence u is analytic as well. Or you can make X complex with r equals to 1, and u is holomorphic. All right, then, so I hope to continue tomorrow then. Thank you very much.